Here we will discuss about some problems on sequence. Let us consider first problem 1. The problem states show that the sequence xn where xn is equal to 1 by 1 into 3 plus 1 by 3 into 5 plus 1 by 5 into 7 up to 1 by 2n minus 1 into 2n plus 1 is monotone increasing, then bounded above. Also show that the sequence is convergent and find its limit. So this is our sequence. We have to show few things. They are, first we have to show the sequence is monotone increasing. Number 2, bounded above and thereby convergent. And lastly, we have to show the limit of the sequence. So we will show all these things one by one. This is an easy problem. First we write xn from the given problem, then express each term in this way: 1 by 1 into 3 as half into 1 minus 1 by 3, then half into 1 by 3 minus 1 by 5, etc. And observe that the each term, its last term of each bracket will get cancelled with the first term of next term. So half into 1 by 3 will get cancelled from first two terms, and in this way ultimately we will get half into 1 minus 1 by twice n plus 1. After simplification, n by 2n plus 1. So if xn is equal to this, replacing n plus 1 by n, we get xn plus 1 is equal to n plus 1 by 2n plus 3. Then subtracting xn plus 1 and xn, we get xn plus 1 minus xn equal to 1 by 2n plus 3 into 2n plus 1, which is positive, as the denominator involving n, which is positive. So xn plus 1 is greater than xn, hence the sequence is monotone increasing. Then to prove bounded above, we express xn. Note this is xn. We express xn after multiplying and dividing numerator and denominator by 2 and obtain 1 by 2 into twice n by twice n plus 1, then adding and subtracting by 1. Ultimately we reach to this step: 1 by 2 into 1 by 2 into 2n plus 1, which is less than half, as this term is positive. So we reach to this point, the sequence is monotone increasing and it is bounded above. Therefore the sequence is convergent. Now to find out its limit, we will show the sequence will converge the limit of xn equal to half. The question is where from this half comes. The method we will follow here, applying this method, only one can show the limit of sequence is equal to some number which we have to consider earlier. How 1 by 2 this term will come in our mind? If we note carefully this term, xn equal to n by twice n plus 1, then as n tending to infinity, as you note here, this n by twice n plus 1 approaches to half. After dividing both numerator and denominator by n, it will give 1 by 2 plus 1 by n, which approaches to 1 by 2 as n tending to infinity. So 1 by 2 is coming from this concept. So we will simply show limit xn equal to half. So xn minus half, mod of xn minus half, it will be less than epsilon. If this is less than epsilon, After simplifying, ultimately we will get if n greater than half into 1 by 2 epsilon minus 1. The right hand side must be some integer. That is why we are taking its integer part and adding 1 with it. Because for particular value of epsilon, the integer part may be 0. For say epsilon is equal to 0.1 or 0.2, if this expression becomes 0.7 or 0.8, something like that, its greatest integer part is 0. But as m is a positive integer, we are adding 1 with it so that it becomes an integer only. So for n greater than equal to m, mod of xn minus half will be less than epsilon for all n greater than equal to m, where m is the greatest integer part of half into 1 by 2 epsilon minus 1 plus 1. If we consider some particular value of epsilon, we will get some definite value of the positive integer n. Say for example, we are considering epsilon is equal to say 0.1. For epsilon is equal to 0.1, this will become 1 by 2 epsilon means 1 by 0.2, 1 by 0.2 means 5, 5 minus 1 means 4, 4 by 1 by 2 means 2, 2 plus 1 is equal to 3. So m will become 3. Similarly, considering other value of epsilon, we will get another value of m means another stage. So ultimately we can conclude the sequence converges and converges to half. Next problem, problem 2. Prove that the sequence xn defined by x1 equal to root 6 and xn plus 1 equal to root over of 6 plus xn for all n greater than equal to 1 converges to 3. So we have to show that the sequence xn where x1 equal to root 6, xn plus 1 equal to root over of 6 plus xn converges and converges to 3. First, if we note it carefully, the sequence, each term of the sequence can be thought as root over of 6 plus previous term. Root over of 6 plus previous term. Here also root over of 6 plus previous term. So we can write xn plus 1 is equal to root over of 6 plus xn for all n greater than equal to 1. Squaring, we have xn plus 1 square equal to 6 plus xn. This relation will be required later. Similarly, putting n minus 1 in place of n, we have xn square equal to 6 plus xn minus 1. Subtracting, we have and factorize, ultimately we get xn plus 1 into xn minus 1 equal to xn minus xn minus 1. See, all the terms of xn are positive. Root 6 is positive, root over of 6 plus root 6 is positive. Similarly, all the terms are positive. So xn plus 1 into xn, first factor is already positive. So the other two factors, if we see carefully, we can conclude that if it is positive, then the next term is also positive. So if xn plus 1 is greater than xn, when xn greater than xn minus 1, xn plus 1 will be greater than xn when ever or if xn greater than xn minus 1. By the same logic, xn greater than xn minus 1 only if xn minus 1 greater than xn minus 2. Proceeding in this way, we can reach xn greater than xn plus 1 greater than xn if x3 greater than x2, that is if x2 greater than x1. So what we can say, xn plus 1 greater than xn if ultimately x2 greater than x1. But it is true that x2 is already greater than x1. Why? Because x2 is square root of a number which is more than 6 and x1 is only square root of 6. So definitely x2 greater than x1. By the same logic, x3 greater than x2, x4 greater than x3, and ultimately xn plus 1 greater than xn for all n. xn plus 1 greater than xn for all n means the sequence xn is monotone increasing. Now, xn square, since xn plus 1 greater than xn, therefore xn plus 1 square greater than xn square. Now xn plus 1 square equal to 6 plus xn. So we can write xn square is less than 6 plus xn. Putting all the terms in the left hand side, we have xn square minus xn minus 6 less than 0, which when factorized gives us xn minus 3 into xn plus 2, that is product of two factor less than 0. But xn plus 2, this factor is always positive as xn greater than 0. So product of two factors negative, of which one is already positive, that means the remaining factor must be negative, that is xn minus 3 less than 0. Therefore we get xn less than 3 for all n. Xn less than 3 for all n means the sequence xn is bounded above and 3 is here an upper bound. So the sequence is bounded above, and already we have proved the sequence is monotone increasing, hence the sequence xn is convergent. Let limit xn is equal to L. We are required to find out what is the value of L. Since limit xn is equal to L, we can say limit of xn plus 1 is equal to L, as xn plus 1 belongs to the same sequence. So from this relation, taking limit both sides, limit x of n plus 1 equal to L, therefore limit of xn plus 1 whole square is equal to L square, and in the right hand side 6 plus L. So L square equal to 6 plus L after taking limit both sides to this relation. So directly we have reached this line, L square equal to 6 plus L. After putting all the terms in the left hand side and factorized, we got L minus 3 into L plus 2 equal to 0. As L is positive, L cannot be negative because all the terms of the sequence are positive. Therefore, the limit of the sequence cannot be negative. So L is positive. As L is positive, so L plus 2 is also positive. But product of two terms, L minus 3, L plus 2 equal to 0. So only one possibility is there, L minus 3 equal to 0, because L plus 2 cannot be equal to 0 as L is positive. So only one possibility is there, L minus 3 equal to 0. L minus 3 equal to 0 means L equal to 3, L means limit xn, so limit xn is equal to 3. Therefore, the given sequence xn is convergent and it converges to 3. Problem number 3. Show that the sequence xn, where xn equal to nth root of n belongs to n, converges to 1. This is first part. And second part is show that limit n tending to infinity 1 by n into 1 plus root 2 plus cube root of 3 plus up to nth root of n equal to 1. So this is our problem number 3. It has two parts. We will first discuss the part A by method 1. By method 1, we know n to the power 1 by n is always greater than 1. So letting n to the power 1 by n equal to 1 plus lambda n, where lambda n is positive. And raising power n, we have n is equal to 1 plus lambda n whole to the power n, and thereby expanding in terms of binomial theorem and retaining only first 3 terms. That is why we have put only greater than equal to sign. We have reached n minus 1 after putting a 1 in the left hand side, greater than equal to n into n minus 1 by 2 into lambda n square for n greater than 1. Cancelling n minus 1 from both sides, we got lambda n square less than equal to 2 by n for n greater than 1, and this is always positive as whole square term. So by sandwich theorem, we have limit of lambda n equal to 0, as limit of 0 is 0, limit of 2 by n is equal to 0. As limit of lambda n equal to 0, we have from this relation limit of n to the power 1 by n equal to 1. Therefore, the sequence xn is equal to nth root of n converges to 1. We can prove the same result using Cauchy's second theorem or limit. Result means limit nth root of n equal to 1. Now, what is Cauchy's second theorem on limit? Let's have a look. If xn greater than 0 for n is equal to 1, 2, 3, etc. and limit n tending to infinity xn plus 1 by xn is equal to L, finite or infinite, limit n tending to infinity nth root of xn will be equal to L. So if xn is positive and limit of xn plus 1 by xn is equal to n, according to Cauchy's second theorem on limit of nth root of xn will be also equal to L. So applying this Cauchy's second theorem on limit, we have by method 2, here we assume xn is equal to n. So xn is always greater than 0 for 1, 2, 3, etc. and limit xn plus 1 by xn equal to limit n plus 1 by n. Taking limit n tending to infinity, it gives 1. So by Cauchy's second theorem or limit, nth root of xn is equal to 1, that is nth root of n is equal to 1. So the same result is proved using Cauchy's second theorem on limit. Now it is required to prove part B. Here we have to prove limit n tending to infinity 1 by n into 1 plus root 2 plus cube root of 3 plus nth root of n equal to 1. To prove this, let's have a look on Cauchy's first theorem on limit, which states that if the sequence xn has a limit L, then the sequence yn, where yn equal to 1 by n into first sum of first n terms of the sequence, has also the same limit L. We now apply here Cauchy's first theorem or limit. We have already proved nth root of n, limit of nth root of n equal to 1, And by Cauchy's first theorem on limit of this quantity is equal to 1. See here, for n is equal to 1, this is 1. For n is equal to 2, we have root 2. For n is equal to 3, cube root of 3. So up to nth term, summing all those nth terms, multiplying by 1 by n, it will be same limit 1. So limit n tending to infinity, 1 by n into 1 plus root 2 plus cube root of 3 plus dot up to nth root of n equal to 1 by Cauchy's first theorem on limit. Number 4. The sequences xn and yn are defined as follows. x1 equal to x plus y by 2, xn plus 1 is equal to xn plus yn by 2 for n greater than equal to 1. And similarly, y1 equal to root over of xy, yn plus 1 equal to root over of xn into yn for all greater than equal to 1 also. And it is also given x greater than y greater than 0. We are required to show that both the sequences xn and yn converge to the same limit. Let us start from x1, y1. x1 is equal to x plus y by 2 given in the problem. And we know arithmetic mean is greater than geometric mean. Here x and y are not equal, so we have not put equality sign here. So this holds, and root over of xy equal to y1 as given in the problem. So we got x1 greater than y1. Again, x2 equal to x1 plus y1 by 2 as given in the problem for n is equal to 1. Also, similarly, as arithmetic mean is greater than geometric mean, we have x1 plus y1 by 2 greater than root over of x1 y1, and root over of x1 y1 equal to y2, which is coming from this relation for n is equal to 1. So we are getting x2 greater than y2, x1 greater than y1, similarly x3 greater than y3, and so on. And in general, xn greater than yn for all n. Now xn plus 1 equal to xn plus yn by 2 as given in the question for all n greater than equal to 1. We put xn in place of yn as xn is greater than yn. We have xn plus 1 is less than xn. We have replaced yn by xn. Similarly, yn plus 1 equal to root over of xn yn given in the question, and putting yn in place of xn and getting yn. So xn plus 1 is less than xn from this inequality, and yn plus 1 is greater than yn from this inequality for all n. Arranging those xn and yn sequentially, we have y1 less than y2 less than yn. Again yn is less than xn, then xn is less than xn minus 1 up to x1. From these inequalities, we have seen that sequence yn is monotone increasing as they are increasing, and sequence xn is monotone decreasing as they are decreasing. Also, yn is bounded above as x1 is an upper bound. As x1 is an upper bound. Here it can be seen that x1 is an upper bound. Again, sequence xn is monotone decreasing for and bounded below as y1 is a lower bound. Y1 is a lower bound. So, yn is monotone increasing and bounded above, xn is monotone decreasing and bounded below. So both the sequences xn and yn converge. Next, it is required to prove that both the sequences converge to the same limit. If not possible, let us assume limit of xn equal to lambda 1 and limit of yn is equal to lambda 2, assuming lambda 1 not equal to lambda 2 if possible. Therefore, in the problem it is given xn plus 1 equal to xn plus yn by 2, taking limit both sides, and as the limit of xn, that is limit of xn plus 1 equal to lambda 1, so this limit will be equal to lambda 1, this will also be equal to lambda 1, and limit of yn will be equal to lambda 2. So we are getting lambda 1 equal to half of lambda 1 plus lambda 2. Simplifying this relation, we have 2 lambda 1 equal to lambda 1 plus lambda 2, 2 lambda 1 equal to lambda 1 plus lambda 2. Therefore, lambda 1 equal to lambda 2. Therefore, both the sequences xn and yn converge, and they converge to the same limit, which we assumed lambda 1 not equal to lambda 2. This is not possible. So, sequences xn and yn converge and converge to the same limit.